All right, so hopefully we might have a few more stragglers coming in, but we're gonna start off. So hello guys, as if anybody joined in the welcoming, my name is Leah, just to reiterate. So for this session, we will be joined by Chris DesRoches. He is the Applied Product Manager of the HVAC division with Mitsubishi Electric Sales. So thank you so much, Chris, for joining us today. His presentation is going to be on commercial air-to-water heat pumps. Just to also reiterate to everyone joining, we do have a Q&A and a chat feature as part of our event website. So that'll be on the right-hand side of your board. I will be monitoring that throughout the presentation. And I will jump in and make sure Chris can answer some of your questions. So I'm going to kick it off to Chris. Go ahead, Chris.
All right, thanks, Leah. So welcome, everyone. Thanks for taking the time out of your busy schedules to be with us today to talk about commercial air-to-water heat pumps. I'd just like to extend my gratitude to the team at Plumbing and HVAC for inviting me here to speak. I've done a lot of talks like this on air-to-water heat pumps because they are a little bit of a novel type of technology that's quickly becoming a buzzword. So certainly if we want to keep doing hydronic systems, but we want to electrify and decarbonize them, then I hope at the end of this presentation, you'll see why air-to-water heat pumps are an important part of the solution. So certainly if you have any questions as we go through, don't hesitate to dump your questions into the chat, and we'll be sure to answer those as we go through. So for today, we're just going to do a recap on air-to-water heat pump technology, just talk about the basics, what we need to consider when we're applying this. And by the way, I didn't mention this before, but all the concepts that we're going to talk about here will extend as well to residential systems, just in terms of the makeup of the system might be a little bit different in the commercial world, but all the core concepts of the design constraints that we're going to look at will apply both to commercial and residential. And then we'll dive into why this is a good fit for electrification and decarbonization, and we'll talk about even some weather data to show how hybrid systems really are a big part of the puzzle as well, as a solution to use both natural gas, just using less of it essentially. We'll have lots of examples as well as we go through them for 2-pipe, 4-pipe systems, as well as cascade systems, and then we'll finish things off with a case study on a retrofit for a chiller upgrade to a reversible heat pump and show you what that looked like, both from an installation point of view and from an economical business case point of view. So we'll dive right into it. So everyone's probably familiar with an air-cooled chiller. This is a device where we're providing chilled water to use in our building in coils and air handling units or fan coil units throughout our building. So in order to do that, we're essentially removing heat from the chilled water portion of the system and rejecting that to the atmosphere through integrated coils on our air-cooled chiller. In the simplest way that we can describe it, a reversible heat pump is just features a 4-way reversing valve on the refrigerant circuit. So we're essentially swapping the functions of those two heat exchangers as part of that machine. So now that heat exchanger that's connected to our building that in summertime is providing chilled water is now acting as our condenser. So we're producing hot water to supply to our building. And in order to do that, we're extracting heat from outside. So in order to do that, we're sending refrigerant that's at a temperature colder than the ambient conditions so that we get heat transfer from the air into the refrigerant circuit. And then through the work of the compressor, we're extracting the heat on the condenser side from that machine and delivering hot water to our building. So heat pump 101, the main metric that we'll use to describe the efficiency or the performance of a heat pump is called the coefficient of performance, or COP, which is just the ratio of the heat output divided by the power input. So typically any kind of heat pump will have a COP anywhere in the range from 2 to 4 or more. So that means if I put 1 unit of electricity into it, I'm getting anywhere from 2 to 4 units of heat out. So if we compare that to an electric boiler, that has a COP that's always equal to 1 for electric resistive heat, whether it's an electric boiler or an electric furnace. And if we're comparing that to natural gas systems, that will always have an efficiency less than 100%. So from an energy point of view, our heat pump, even at its worst case design conditions, is still at least 200% efficient. So it can make a lot of sense. So if we look at just commercial buildings, 2-pipe changeover systems, this is the example that I always like to say. Out of the city of Toronto, we have a lot of condo buildings, and those typically feature a 2-pipe changeover system, meaning in the summertime, we'll use our chiller to provide chilled water, and we'll supply that to our fan coil units inside the building. We'll supply them to coils and air handling units if we have those in the building. So what's important with the 2-pipe system is we're providing chilled water to everything in the building at any given time, or hot water in the wintertime from our boiler supplied to everything in the building. So usually with 2-pipe systems, we can have heating and cooling at the same time. If we do require that in our buildings, we'll have what's called a 4-pipe system, which is essentially just two-pipe systems stacked together, one dedicated for cooling and one dedicated for heating. So if we have a reversible heat pump, a device that can produce hot water and chilled water, then why don't we use these types of machines more often? So there's a lot of different reasons for this. The main reason is the economics of it, of natural gas versus electricity, which has significantly shifted in recent years, as we'll see in later on in the presentation. But again, like I'll mention this right now, with any air to water heat pump technology, if you're looking for that silver bullet that's going to provide 100% of your heating capacity on the coldest day of winter, if you're in Saskatchewan at -40, there's no air to water heat pump on the market right now in the commercial space that can provide hot water down below -20 degrees Celsius or so. So for most of these systems, you're going to require electrical backup as electrical or gas boiler backup, as part of that. So really, to leverage this for the most amount of time during the winter or the shoulder season, that's really where air to water heat pumps will shine. And we'll still have that auxiliary boiler to use on the very cold winter days. So really, if you're working with engineers or designers, what's important is to understand the capabilities of the heat pumps. In terms of the cooling operation of these types of machines are very similar to conventional air-cooled chillers. They'll operate with similar delta Ts. It's really on the heating side where they're a little bit different than designing with conventional boiler systems. So it's really important to understand the main constraints within the operation of air to water heat pumps and how that's influenced by ambient temperature. So we're going to dive into the basics here a little bit and just talk about how the ambient temperature will influence the heat pump's operation and how we can design around that and still implement it within our systems. So really, there's kind of 3 key factors that we need to look out for with air to water heat pumps. And how the ambient temperature will influence that. The first one is the supply temperature reduction, which is referred to as our operating envelope. So contrary to a boiler that is able to provide you a fixed supply temperature at any given time, the ambient temperature will impact the supply temperature you can generate from a heat pump. So obviously, from a design point of view, this could be challenging. So we're going to need to design with the lower temperatures is the end story here, and we'll talk about that on the next slide. The other thing, because we're using a refrigeration circuit to extract heat from outside, the colder it is, the harder it is for the machine to extract heat from outside. So we're going to have a reduction in capacity. And the third point is our coefficient of performance is also going to reduce. If our coefficient of performance is the capacity divided by the power input, if our capacity is reducing, then so will our coefficient of performance. So the first one, the operating envelope. So shown here is the operating envelope for conventional commercial air to water heat pump technologies that are available on the market. On the y-axis here, we have our heating supply temperature. And on the x-axis, we have our ambient temperature. So if you look at any manufacturer's catalog, they'll say hot water as high as 55 or maybe 60 degrees Celsius, which is true. But whenever you look at the detailed operating envelope from any manufacturer, you'll see that, yes, this is true. You can generate 55 degrees, but only at an ambient condition of about 3 to 10 degree ambient. As it gets colder from 3 degrees, your supply temperature will start to decrease. So typically these commercial air to water heat pumps can generally provide you about 45 Celsius leaving water temperature, which is 113 Fahrenheit, down to about -10 Celsius ambient, which is 14 degrees Fahrenheit. Typically, machines will operate down to -15, maybe -20. The products offered from Mitsubishi Electric currently operate down to -15. But you can find some other ones on the market that will maybe operate down to -20. But for example, if we're designing in the city of Toronto with a design temperature of -23, well, if the heat pump can't work below -20, then you're still going to need an auxiliary boiler. And we'll talk later about how that can provide some significant advantages as part of implementing these systems in a real world application. But just for perspective, according to the ASHRAE data for Toronto, the 99.6% winter design temperature is about -18.5. So this means that we only spend 0.4% of the time below -18.5 degrees Celsius. If we look at the 99% value for the city of Toronto, this is -15.7. So we only spend 1% of the time below -15.7. So obviously designing with boilers is very easy. If we're designing with condensing boilers, we'll typically pick a supply temperature of 140 with a 20 degree Fahrenheit delta T. which is roughly 60 degrees Celsius supply and 50 degrees Celsius return. So there's kind of two trains of thoughts. We're seeing trends now in the hydronic world where we're seeing lower and lower design temperatures. We're seeing, fan-assisted convectors that can get a little bit more heat output, and those can be selected to operate with lower supply temperatures. So usually the go-to point that I recommend to designers is to try to design your system for about 45-degree water, because that's a good balance between having a consistent supply temperature. We don't want to worry about how our supply temperature is changing as it gets colder outside. So picking a fixed supply temperature from the heat pump can generally simplify our designs, and it can also simplify the controls. So that's really just a balance between having a temperature that we can get this temperature consistently versus having a temperature that's warm enough that we can actually get good heat transfer in conventional heat emitters. So that would be point 2 here. But if we're talking about new construction where we're able to select our heat emitters and we want to do a low temperature system, then whenever we switch over to the backup boiler, we can still use that at a low temperature, and that's just going to ensure that we have an optimal efficiency on our boiler system as well if we're using natural gas. If we're a little bit more constrained and we're doing a retrofit application, then maybe it's not practical or feasible to replace all the heat emitters in the building. Maybe there's budget constraints. Maybe you don't want to disrupt, the tenants or occupants in different zones, depending on the building type. But an important point to remember is that with boiler systems, generally, if we're designing for 140 degree Fahrenheit or 60 degrees Celsius, that's our design temperature on the coldest day of the year. But usually as it gets warmer outside, we have less heat losses from our space. So we actually decrease the supply temperature going out to the building anyway by using outdoor reset curves on our boilers. So if we think about a retrofit and we already have an outdoor reset curve as part of those heat emitters, then you could potentially find a natural intersection between the supply temperature between the heat pump, where you're going to use that maybe down to -5 in some cases with 50-degree supply. Really depends on the specific system. But the main message is we're going to try to design with lower temperatures as much as possible. And we'll talk about heat emitters in a couple slides as well in more detail. The second point to consider is our heating capacity. So our heating capacity is going to change as it gets colder. So what's important to recognize if you're looking at a manufacturer's catalog, they'll say hot water up to 55 degrees and they'll give you a capacity. But it's also important to recognize that that's based off standard AHRI rating conditions. And currently those AHRI 550 rating conditions are based on 8.3 degrees Celsius ambient temperature. So this is kind of at the tail end of heating season. If we're up above 15 degrees, we don't really require much heating in our building anyway. So if you look at this capacity curve for the heat pump here shown in blue versus a heating load profile for a building, obviously at the coldest temperature, that's where we have our maximum heat load shown here in percent. But as it gets warmer, we have less than 100% of that load that's required. So if we base our capacities based off the AHRI conditions, you would look at this point here and say, okay, well, I have about 145 kilowatts of capacity, but I have maybe 40% of the total peak load that's actually required in the building. So you could look at this and say it's undersized, but depending on the supply temperature you're going to design with, you would essentially try to match as much heating capacity depending on the design again as possible. So here in this example, this would show sizing the heat capacity at -15. So this is if we're using a lower water temperature of maybe 35 or 40 degrees Celsius. But really in most practical installations, we're actually going to switch over depending on a couple things. And this is called a bivalence changeover. And bivalence just means we have two energy sources in the building and we're going to use both of them according to the design of our system. So in this slide here, we can decrease the initial sizing of our heat pump, maybe pick smaller units by factoring in this bivalence temperature. And to be honest, in a lot of cases where we have hydronic heating and cooling, really where this type of technology shines is going to be sizing them for the cooling capacity and using it as much as possible in the wintertime and supplementing any missing capacity with an auxiliary boiler. So in this example here, this shows a bivalence temperature of about -8 degrees Celsius. So this would correspond to having about a 48 degrees Celsius supply temperature. So that's one of the criteria that will dictate when you switch over. If you're fixed to say, hey, the lowest temperature that I can use in my hydronic system and my heat emitters is about 50 degrees. If the machine can give you 50 degrees supply down to -5 ambient, then you'd switch over below -5. Here, if you would say, well, we can live with 48 degrees supply, keeping in mind that we don't have huge heat losses from our space at -5 or -8, sorry, compared to -23. So really it's the heat envelope of the building that will also kind of dictate the maximum supply temperature that we can, or sorry, the minimum, I should say, that we can work with the heat pump before cutting out. Or the second consideration that we might have is we might determine the COP that we want to run the machine down to. So if we said, well, we don't want to operate the heat pump when the COP or efficiency is less than 2, then it's more cost effective to run off natural gas below a COP of 2. Then that could also dictate where you're switching over to the auxiliary gas system as part of that. So kind of two ways you can think about it, but really dual fuel system provides you the flexibility to run your system off the lowest operating cost if that's what your clients are looking for, or operating it off the lowest carbon footprint, or doing the most amount of fuel switching as possible. So it does still provide some flexibility. The third thing that will change is our COP. So we talked about this before. So this chart is actually showing us the bin hours for Toronto. So there's 8,760 hours in any given year. And this is showing our distribution. So we're looking at how many hours do we spend at -23, how many hours do we spend at -15, how many hours do we spend at -9, and we get this load profile here. And we'll have weather data in a couple slides that's going to show different climates across Canada and how many hours we actually spend between -10 and +10, which I like to refer to as good heat pump weather. So yes, Toronto does get down to -23 at coldest. This past winter, actually, it dipped down close to -30 for a couple days when we had a really bad cold snap. But yes, it gets cold, but we spend a relatively infrequent amount of time actually spending in those extreme cold conditions. So what this chart is also showing us is the efficiency for an air-to-water heat pump at different operating temperatures. And really the main message here is the lower the supply temperature you can design your systems with, the more efficient the heat pump's going to run. If it's making 45-degree water versus 35-degree water, obviously to make 35 Celsius water, the machine doesn't need to work as hard. It's going to be more efficient. So if we just compare a milder winter day of about 0 degrees, if we're designing with 45 degrees versus 35 degrees, we'll have a COP at 45 degree supply of 2.8. But if we're designing with 35 degrees, we'll have a COP of 3.4, which means it's about 20% more efficiency. So generally, when we're talking about using low temperature heat emitters at 35C, you're probably talking about radiant and force systems designed with lower temperature. One of the common arguments against radiant and force systems, as much as they are one of the most comfortable ways you can heat an indoor space, especially spaces with very high ceilings as well. One of the arguments is it's very, sometimes cost prohibitive. They're a lot more expensive to install than simple fan coil systems. And this is true, but we need to kind of separate the ideas of operating cost versus first cost, because although the radiant and force system might be more expensive to install as a first cost, if you're going to have 20% efficiency improvement over the life cycle of that equipment, then it can kind of make up for those differences in cost savings. So that does need to be factored into the decision as well. These leaving water temperatures as well are kind of showing us our operating envelope. So if you remember from the first slide, when we talked about operating envelope, we said, well, you can generally generate 55-degree water between 3 and 10 degrees Celsius ambient. That's why this line's starting and stopping at 3 and 10. So if you're designing with 50-degree supply, typically with this technology, you can get about 50-degree supply down to -5 or 45 Celsius water down to -10. So that's why these lines are ending there. So this is also the lower temperature you can design with, the more hours you're going to be able to cover essentially on the lower end here and still be able to use less and less boiler with 35 degrees here. So if we look across Canada, if we say an air-to-water heat pump at best can work down to about -20, well, unless we're in Victoria or Vancouver, which are mature air-to-water heat pump climates. It's actually interesting. Vancouver and Victoria are actually predominantly now air-to-water heat pumps in those climates. Southern Ontario, we're a little bit milder, and the Maritimes, we are a little bit milder. But if we're talking about the prairies or Quebec, our design temperatures are well below -20. So we'll need to look at hybrid systems, whether we're using backup gas or electric as part of that. But still, when we use within the heat pump range where they can operate, we can still have some good savings. So just to kind of summarize it, this is the data for Toronto. So kind of grouped into medium to high temperature applications. in which case you'd want maybe a 50-degree supply temperature, which you can use this type of equipment down to about -5. So in the high temperature range, below -5 on average for the last 4 years for the city of Toronto, we only spend 682 hours below -5. So about 7.8% of the year, but between -5 and +10, Toronto still spends about 47% of the year between that. So that's the prime of heating season where the air to water heat pump can still decarbonize a lot of that heating load to shift it to electric heat pump over gas. If we're talking about medium temperature applications, maybe you could do a little bit of a lower supply temperature in your system of 45 degrees. You can now run the heat pump down to -10. And now we're still using that heat pump between -10 and +10 for 52% of the year. And we're only spending 200 hours below -10, so 2% of the year. And if we're designing with a really low temperature, so, domestic hot water preheating, low temperature radiant in-floor, or maybe some type of cascade system, now we're talking about only about 44 hours that Toronto spends on average below -15, so 0.5%. And now the total time between -15 and +10 is about 55% of the total year. So obviously Toronto's a little bit more of a milder climate, but just to kind of put this in perspective and be a little bit critical, presenting here kind of from the best climates in Canada to kind of the harshest climates in terms of winter heating. So Vancouver's obviously very favorable. Their design temperature is about -7, -8 degrees Celsius. So they don't actually need backup in a lot of these systems that are going up in the city of Vancouver now. And they spend 50% of the year between -10 and +10. If we look at Montreal, a little bit colder than Toronto, if we're talking about -10 cutout temperature, Montreal still spends 50% of the year between -10 and +10, about 586 hours below -10. If we're designing with maybe a warmer temperature in the system of 50 degrees and a cutout temperature of -5, Montreal spends 1,300 hours, a little bit over 1,300 hours below -5, so 15% of the year. But between -10 and +10 is about 3,600 hours, so 41% of the year. And if we go to kind of the prairies, Calgary and Saskatoon, obviously they're a little bit more harsh, but even Calgary as an example, if we're able to design down to -10 changeover temperature, we can still cover off 52% of the year between -10 and +10 with a heat pump. And similarly for Saskatoon, about 46% of the year. The number does go down a little bit if we're designing with a warmer temperature from the heat pump of about 50 degrees Celsius. Now we're talking about 35% of the year in Saskatoon below -5. And for Calgary, about 31% below -5. And for Calgary, 18% below -5. So this is just to kind of illustrate, we do still need hybrid systems with natural gas supplementing it, but we're going to try to cover off as much of the heat pump as possible. And depending on your climate, this can make more sense in favorable climates and maybe not as much of a compelling case in prairies like Saskatoon, but just trying to provide the full picture. So what does this mean for heat pumps from a carbon point of view and an energy point of view? Well, if we want to keep doing hydronic systems and we don't want to go with VRF systems, or if we don't want to go with packaged heat pump air handling distribution, hydronics are still very flexible in being able to kind of build your system like Lego blocks, essentially. If we want to keep doing hydronics, but we want to decarbonize and electrify those systems, what are our other choices if we want to get away from natural gas? Well, natural gas always has a COP less than 1. Typically with a condensing boiler, we'll have an efficiency of 95 to 98% efficiency, but really the return temperature will determine that. But it's always going to be less than 1 with natural gas because we will have some losses in that system. And, a big portion of the market, seems to think, well, let's just change all the natural gas boilers to electric boilers. You could do that if you have enough electrical capacity on site. But frankly, it's not a scalable solution. There's not enough grid energy to be able to switch all the boilers from gas to electric. Not to mention, the amount of electric car charging that we're going to see in the next decade as well. But you could, depending on the client's requests, drives and level of investment that they're willing to make, and if they can get enough power from the local utilities, then they could change it out to electric boiler. But that's still an efficiency of 100%, which is technically better than the gas boiler, but you're fixing your system to all electric at that point. With an air to water heat pump, though, you'll have a COP anywhere from 2 to 4 or more. The only drawback with this is that you have limitations on the maximum supply temperature and the cutout temperature that the air-to-water heat pump can give you. But if we can design around that, taking into account the concepts that we talked about on the preceding slides, then we can still get a lot of good value on that and use backup gas or electric as part of our system. So from a carbon emission point of view, what does this look like? So if we look in Ontario, unfortunately, over the last 2 years, emissions in Ontario have gone up. So in 2020, the average emission factor for electricity in Ontario was about 30 grams of CO2 per kilowatt hour of electricity. And that's roughly doubled now in 2023. So this is the AEF, which means average emission factor. And this is an estimate from TAF, the Atmospheric Fund. And their 2023 estimate average CO2 emissions is about 0.07 kilograms or 70 grams of CO2 emitted per electrical kilowatt hour. And if we take our natural gas and we convert this to kilowatt hours of natural gas, producing this same amount of thermal kilowatt hours for a building will produce 186 grams of CO2. So this chart here is actually taking into account electric heat pump, electric resistive heat, so an electric boiler, and natural gas, and we're normalizing the emissions to produce the same amount of heat in kilowatt hours, and we're comparing that and we're normalizing it to the heat pump. So we're essentially expressing, at -10 with a lower supply temperature from the heat pump, how many more times emissions are associated with using electric resistive heat or natural gas. So at -10, when the heat pump has its worst efficiency, quote unquote, the electric resistive boiler is still about 2.2 times more emissions to produce that same amount of heat. But at +29, it's about 4 times more emissions. And so this is essentially our heat pump coefficient of performance, because our electric resistive boiler has a COP of 1. So if we're dividing a COP of 1 by the heat pump's COP, then it's essentially going to give us the COP curve for the heat pump. If we compare that same point at -10 to natural gas, that's still 7 times more emissions when our COP is at about 2.2 from the heat pump to produce that same amount of heat. But at +30, when we can get really good efficiencies from the heat pump, COPs of 4 or 5, then up here in this range, we're 12 times more emissions to produce that same amount of heat with natural gas. So this is for Ontario, where our emissions are about 70 grams CO2. Obviously, the grid is a big factor in the amount of decarbonization that we can get with air-to-water heat pumps. If we look at British Columbia, they have a very clean electrical grid. Their electricity is about 18 grams of CO2 per kilowatt hour, and a little bit dirtier natural gas consumption with the supply out there. But for that same comparison, just looking at natural gas, we were looking at this point -10. Well, in British Columbia, based off their cleaner grid, that number goes up to 25. So there's 25 times more emissions to produce that same amount of heat with natural gas. And we're in the warmer parts of the summer, that can be up to 47 times more emissions whenever a heat pump has really good coefficients of performance. If we look at Quebec, which is virtually zero carbon, for that same electric kilowatt hour, that produces 1.2 grams of CO2. They get most of their energy from hydro. So if you make that same comparison, you can't even see the electrical resistive heat curve there. And that's one of the reasons why Quebec is predominantly an electric heat market. But even at -10, we're now talking 360 times more emissions associated with natural gas, and on the warmer days, upwards of 700. So obviously, these are for the favorable electrical grids in Canada. Currently, Alberta has an emission factor average of about 400 grams. So in Alberta today, with a heat pump, unless your COP is above about 2.3, it's actually worse for the environment to run a heat pump in Alberta. Similar with Saskatchewan and Nova Scotia, evenly, those are kind of three of the outliers that do have higher emissions, but we know that they're going to clean up their grids over time. So certainly, as these jurisdictions clean up their emissions on their grids and adopt, nuclear or wind and solar energy, this is going to continue to make it more favorable in those markets as well. So coming back to the example for Toronto, which is one of the examples that I had prepared. So if we just look at doing a fuel switch down to -10, So this is an arbitrary building load profile. So if we do an entire hydronic system with all natural gas shown here in red across all these bin hours, or do this entire load profile with an electric boiler, or some combination of fuel switching. So using the heat pump up to about 18 degrees in heating season, down to -10 only, and then using backup gas or electric. If we're gonna use the heat pump in this fashion, we can still offset, just in this green triangle here, about 156 tons of CO2 offset per year. So on a chart, if we just look at total annual emissions for the load being served by a gas boiler here in red, we'd have pretty close to 200 tons offset per year. If we switch that to all electric, we'd have a little bit over 50 tons of CO2 offset per year. But any combination of the hybrid system with air-to-water heat pump and backup gas or electric will still have substantially lower emissions as part of that. So although the heat pump's not going to be the silver bullet for the system to cover off all of heating season, even during that window where we are using it between -10 and +10, where we have good heat pump weather, we can still significantly reduce the building emissions and just using natural gas on these colder portions here. From just an energy point of view, so if we take all that energy to meet that building load profile that we showed here, and offsetting with a partial fuel switch in this green triangle here from the heat pump. So that's heat pump is shown here in green, electric boiler shown in yellow, and natural gas is shown in red. So if we're meeting 100% of this load just from a gas boiler, this is assuming 95% efficiency always. If we take that load times the bin hours, times the efficiency of the boiler, and convert everything to kilowatt hours, to serve this arbitrary load profile with natural gas will be just over 1 million kilowatt hours. And if we change that to an electric boiler, we'd have about 880,000 kilowatt hours because our boiler is 100% efficient. So really the difference between electric boiler here in yellow and the gas boiler is that extra 5% efficiency. But any combination of the partial fuel switch, where we have a COP from the heat pump here of 2, we have a COP here of about 3.5 and around 3 here. So we're basically shrinking a big portion of those bin hours because we have the efficiency that's 200 to 300 or even 350%. We're shrinking a big portion of those kilowatt hours and then supplementing the rest here. So below -10 for Toronto, I said it was about 200 hours we spend below that. So this is the amount of energy that's used on the natural gas side to produce heat for those 200 hours. But the rest of the year, we're operating off the heat pump. And the same goes for electricity. So, we saw on the last slide, we can significantly reduce our building emissions, but we can also reduce total energy consumption. So this is a big advantage for energy modelers, because for new construction, we're starting to see more and more stringent codes where we have our thermal energy intensity demand, TEDI, and we also have our GHGI, or greenhouse gas emission intensity. And while those might be modest targets to do a high efficiency cutting edge building today of, say, 20 kilograms of CO2 emitted per square meter of building space, well, by 2030 for near net zero buildings, that value for commercial office building in Toronto goes from 20 kilograms CO2 today to 5 kilograms of CO2 per square meter by 2030 for a net zero ready building. So essentially what this means is we need tighter building envelopes, but we need to eliminate natural gas from the system as much as possible, and maybe just use natural gas for the peak days. So air to water heat pumps, to kind of summarize, not only make sense from an environmental point of view with carbon, but also from an energy point of view and meeting energy modeling targets that we need for new buildings. It is an important tool from an energy point as well. So sorry about boring everyone with all the math, but we're going to get into some piping and applications now. So for heat pumps, I hope everyone learned throughout, those examples of why air to water heat pumps will be a critical tool moving forward. But now everyone's probably wondering, well, how do we use it in conventional systems? So really the low hanging fruit for this type of equipment on today's market, considering everything, is chiller retrofits. So if you have any chillers that need to be replaced, instead of just replacing like for like, you're going to be stuck with that asset over the lifespan of that new chiller that's put in. So it can make a lot of sense to upgrade to the heat pump and put it to work in the winter instead of shutting the chiller down and offsetting some boiler usage with natural gas as much as possible. Depending on the system that we have, we can get different advantages. So I do like to group them into low temperature heating applications and kind of medium temperature heating applications. Another really good system that you can implement air to water heat pumps in are water loop heat pump systems. So just shown here, this is also common in condo buildings in Toronto, where maybe in each suite you'll actually have a terminal unit. These are also common in commercial office buildings. So this is a really good way to provide 4-pipe comfort. All these different zones can individually be in heating mode or cooling mode, but we're getting 4-pipe comfort with only 2 pipes of distribution throughout the building. So typically, the best way that you could implement the system would be geothermal. So coupling these compressorized units to a ground loop. But geothermal can be very expensive, can require a lot of space. But especially for retrofit systems, it's not always practical or feasible to retrofit a geothermal well in an existing building. So typically, if you're not able to do these systems geothermal, then typically they go cooling tower boiler. And now with decarbonization trends, people are looking for an alternative to that natural gas boiler in that system. So air to water heat pumps can make a really good fit into that system to be able to add heat into the winter over a natural gas boiler. And because these systems in wintertime operate with very low temperatures, 25 to 30 degrees Celsius, somewhere in the neighborhood of 80 degrees Fahrenheit, this means that we can maximize the efficiency, and we can also use the heat pump down to a very low temperature of minus 15. And depending on how many hours you spend in your local climate below minus 15, you'll supplement with natural gas boiler below that. Domestic hot water preheating is another really good application that we're starting to see a lot more of in the market. I'll touch on that later. We have a couple slides on that. Ventilation preheat or maybe snow melting as well can be good applications to use a low temperature from the heat pump. And then if we're talking about medium temperature applications, we're talking about fan coil units, cabinet heaters, things like that, where maybe we're going to design with a 45 to a 50 degree supply temperature. So certainly if we have existing hydronic air handlers as well, we can produce hot water to use in those. And maybe in a retrofit application, we can just resize those coils to have more surface area and use a lower supply temperature to match our capacity in those air handling units. I just wanted to show this slide. I'm sure a lot of you have seen this going around through the industry. Credit to John Siegenthaler. This is one of the topics that he's promoting as well, with future-proofing hydronic systems, designing with lower temperature supply temperatures and systems. So panel radiators and ceiling and wall heating and radiant infor are really good ways that we can efficiently and comfortably heat our spaces, but also use lower temperatures that are compatible with kind of the design criteria that we need from the heat pumps. I can't tell you how many phone calls I get about someone who says, hey, I have a 2 million BTU boiler with 180 degree Fahrenheit. We would like a heat pump, please, for this application. There's no heat pump really on the market that will give you 180 degree supply, unfortunately. If there's anyone on the R&D side on this call, please make a heat pump that will do high delta T's and high supply temperatures. I think for the retrofit market, that's definitely something that is in dire need in our market. You can do it with a cascade system that we'll talk about later if we have time. But generally for those, cast iron radiators or high temperature fin tube baseboards, you're not going to be able to use 110 Fahrenheit supply temperature in that system and get the same heat output. So for retrofits, we might need to change those heat emitters in our building. But certainly for new construction, even if you're not convinced on using air to water heat pumps, there's still benefits with gas systems of using lower supply temperatures in those systems. So certainly future-proofing our buildings and using lower supply temperatures can provide a lot of benefits as well. And now you can install the heat pump into this after. I just wanted to talk about forced air fan coil units, in particular changeover systems. So in Toronto, and we'll talk about a condo retrofit that Mitsubishi did in the city of Toronto. But vertical stack fan coil units are very popular in the city of Toronto. And a challenge as I see it in the market is a lot of engineers or contractors, they're doing retrofits and they'll look at the nameplate and the original selections and they'll try to match new systems with those old parameters. But we know from these older systems that they're often oversized. But if we want to add value to our clients in the marketplace who are looking to transition to low temperature air to water heat pumps, then we do need to think a little bit more qualitative about this. And I used to work in the vertical stack fan coil world, and especially in two pipe changeover systems, what I would see all the time, in designs going back 10 years ago, engineers are always sizing the coils in fan coil units and changeover systems, whether it's vertical stack or horizontal ducted type fan coils. The coils in those machines are always sized for the cooling requirement so that you can maintain the appropriate amount of sensible heat ratio in that, so you can do some dehumidification. So typically with those fan coil units, you'd select it based off the cooling requirements for the spaces, and you'd end up with 3 or maybe a 4-row cooling coil inside that fan coil unit. And then they would, in heating mode, they would just rate them using the boiler supply temperature that they're using and rate that at 160 or 180 Fahrenheit. The point I'd like to make here is if you were going to select a fan coil unit for heating only application, if you're using 160 or 180 degree Fahrenheit water, you would probably only be selecting a 1 or a 2-row heating coil to go in that fan coil unit to meet the heat load requirements. But what they would do is select the fan coils based off cooling, use a very high boiler temperature, and this actually causes a lot of temperature swings in the spaces, because with 180 degree water with that 4-row changeover coil, you get tons of capacity out into the space. So in reality, the fan coil unit's just short cycling that valve all day long, blasting out hot air, turning off, causing some drafts in the space. So when we did this condo retrofit, we looked at the fan coil heat emitters and recognized that the coils had more surface area on them. And while using a 45 degree supply temperature through an existing coil with more surface area, that's all we're trying to do in a hydronic system, is match the heat loss of the space. A kilowatt's a kilowatt, we're just delivering it at a lower temperature. We might see with a lower supply temperature on the hydronic side, maybe a little bit of a lower discharge air temperature on our fan coil unit, but the concept is with a lower temperature through these coils, the fan coil units just run more time matching the heat loss of the space. And then certainly as it gets colder down to -15, maybe the heat pump shut off, we can fire up the boilers, and we're not necessarily constrained to use the same supply temperature with the boiler as we were with the heat pump. So we do need to kind of try to avoid just doing like for like and matching things off nameplate. I know everyone likes to do that so that they don't get sued. But if we want to add value and we want to make significant change in our market, this is something that we're going to see a lot more of in the design build community, I think. So 2-pipe systems, most times we're going to size the units based off the cooling requirement. So here in this example, in a 2-pipe changeover system, we would have 1 or more units required to meet up the total cooling capacity, and we'll stage those on and off during the cooling season to meet our peak demand. We'll have a seasonal changeover valve to switch over to the boiler during winter, which is what we see here. So again, most of the time you're going to size these based off the cooling requirement, and whatever you get out of it in heating you can supplement the rest with the boiler. It really just comes down to capital investment. If you want to meet more of the heat load in your design parameters or within the capabilities of the heat pumps, maybe you want to add a 4th unit in heating, you could do that. It's just more capital cost. If it's only going to run for an extra 2 or 3% of the year, maybe to meet the building heating demand requirements, for an extra couple hundred hours throughout the year, are you going to make that capital investment for a 4th machine? You could add another unit, but oftentimes, because we spend a relatively low amount of time, it really depends on the bivalence temperature that we're looking at based off the characteristics of our building. So most cases, it just simplifies a lot of the controls just to get as much heat from the heat pumps as we can and supplement the rest with the boiler. So here with auxiliary boiler heating, this is maybe a colder day where we're running with the boiler. You could design your system to run with the heat pumps and the boiler at the same time to have the boiler provide missing capacity. You just want to be aware that the heat pumps and the boiler should have the same supply temperature because really it's the return temperature to the heat pumps that will dictate whether or not it's going to be able to run in the system. And we'll have an example on that towards the end of the presentation. We were talking about 4-pipe systems as well. So a lot of systems nowadays are turning more towards 4-pipe systems with heating and cooling required sometimes year round, especially if we're doing VAV systems where we might have individual spaces that need to be in heating or cooling even in the winter. So a 4-pipe system is just two 2-pipe systems stacked together. We can still use heat pumps in it. There is a class of equipment of what's called 4-pipe simultaneous heating and cooling heat pumps. And these machines are able to generate heating or cooling or anywhere in between with a bit of heat recovery. Those are good solutions if you do have an actual demand to use hot water. But I'm really seeing the market shift now more towards using 2-pipe heat pumps, which are going to be much more efficient at full load heating or full load cooling than a 4-pipe simultaneous heating and cooling heat pump will be at full load heating, full load cooling. In British Columbia, as an example, a couple of years ago, we used to see these 4-pipe units, big high-rise towers with 300 tons of cooling capacity of 4-pipe units. And the way engineers will look at that is say, well, I can do 100% heating, 100% cooling, and anywhere in between. But the load profiles, what they're seeing now is, you might have 300 tons of cooling that's required in summer. And in heating, you might only have 25 to 50 tons of heating that's required at that same moment in time. So now what they're doing is maybe using a heat recovery chiller or a 4-pipe simultaneous heating cooling heat pump and size it for the base load heating capacity. So what we're seeing now is they'll do 50 tons maybe of those 4-pipe units or 50 tons of heat recovery chillers and 250 tons with 2-pipe heat pumps. You can actually use 3-way valves on these heat pumps, and we're designing several projects with this type of heat pumps, where by putting 3-way valves on the inlet and outlet of each unit and some controls, we can coordinate whether or not the heat pump's running in heating mode or cooling mode and working to the hot water circuit or to the chilled water circuit. And again, because of the operating envelope constraints, 98% of the time you're going to need an auxiliary boiler anyway. So in this type of system, you'd size the heat pump units based off the cooling requirements and stage them according to the cooling requirements of the building. And depending on the load profile requirements, any units that don't need to be in cooling can be staged to heating to offset any natural gas usage. And then an auxiliary boiler just tops up any missing capacity. So we're starting to see more systems like this come out as engineers start to get a little bit more creative about trying to still find low cost and simple solutions to decarbonize and reduce boiler operation from natural gas. I talked about cascade systems, and I'm not sure if everyone's familiar with a cascade system. When I say that, cascade system simply means we're using a heat pump to provide the input to another heat pump. So one good application, as I was mentioning earlier, is water loop heat pumps or even water-cooled VRF as an example here. So without going into the details of VRF, I think everyone's familiar with that, but my focus is really on the hydronic side. I think VRF can be a good solution depending on the building. But in simple terms with VRF, heat recovery VRF systems are able to essentially recover heat between individual zones connected to a branch box controller. And so this is all refrigerant done through these indoor units in different zones. And that refrigerant are coming from water-cooled condensers. So with a heat recovery VRF system, we're actually getting two kinds of heat recovery in our system. We're exchanging heat between individual zones connected to a common branch box controller. But then also on the water distribution side, if we pretend that, say we're doing 4x4 VRF, so you have one floor above us, let's say, that's cooling dominant. So now we're extracting heat from this water-cooled condenser on the floor above us. But say the water is now coming down through that riser down to our floor, and our floor is heating dominant. Well, we're actually just exchanging heat between these water-cooled condensers. So we're kind of getting two layers of heat recovery. And then you could have this system tied to geothermal. But when geothermal is not feasible, we can do it through air-to-water heat pumps. And now this is acting as a heat injector or a heat rejection device as part of our system, whether the entire system is cooling dominant or if it's heating dominant. This application is also good for the same reasons I mentioned before about water loop heat pumps, where This just needs really low grade heat. And we're actually designing several systems as well with VRF systems that are now using air to water heat pumps to provide the heat input and the cooling rejection. Same concept, but for maybe water to air units. So water furnace as an example. These are going to heat up air with a refrigerant circuit inside these machines. So if you didn't want to do the full VRF system, and maybe condo, high rise with water to air heat pumps, that can still use an air to water heat pump as the heat injector with auxiliary boiler just for those few hours that it's needed to run. The last topic I wanted to cover off in the next 8 minutes or so is domestic hot water. So we're starting to see more trends with electrifying domestic hot water, and we're seeing more heat pump products, especially using CO2 refrigerant, which is a totally different animal. CO2 heat pumps want to see really high temperature lifts, and they're good solutions. They just need to be sized with a lot of storage in those systems. But if we think of the conventional way we do hydronic domestic hot water heating, we'll use an indirect tank typically for that. So this is an example I always like to go through to kind of illustrate that. So if you want a heat pump to be able to produce domestic hot water, you want the heat pump to have maybe a 60 or 65 degree supply temperature to add heat into that domestic hot water tank, because we maintain domestic hot water at 60 degrees for Legionella, and that's a code requirement that we have here in Canada. So in the basic way that we've seen a lot of people using air to water heat pumps, maybe if there's other manufacturers that are making 60 or maybe 65 degree water, we'll couple that to an indirect tank, and we'll have the heat pump producing water in this tank, and we'll have a boiler on that as well for auxiliary heat. In the conventional way though, the ability of the heat pump to add heat into this domestic hot water tank depends on the temperature of the water in the tank that we're heating, and it depends on the temperature of water that the heat pump's able to generate at any given moment in time, according to the operating envelope. So, for example, if we look at a multi-unit residential building, those buildings are very cyclical. Everyone's getting up at 7, 8 o'clock in the morning, having a shower before they go to work. So suppose we have a huge draw from our hot water tank. So this water that was stored overnight at 60 degrees gets depleted by 50%. Now we fill that up with domestic cold water coming from our city at, let's call it 10 degrees Celsius. So in that example, our tank is at about 35 degrees Celsius. So the heat pump's ability to add heat into this tank, well, it needs to provide water that's hotter than 35 degrees so that we can transfer heat into this tank. So if we look at the operating envelope for the heat pump unit, you would look at it and say, well, if I want 45 degrees from the heat pump, or maybe even 40 degrees if we forget about approach temperatures and how things are changing as we're adding heat to the tank. Say if we wanted 40 degrees from the heat pump to be able to add some heat into that tank, well, we'd say, okay, well, we can use this down to about minus 12 degrees Celsius. In reality, though, as the tank warms up, the heat pump supply temperature always needs to be at least 5 degrees above the tank temperature to get heat transfer into it. So, but for argument's sake, you could use the heat pump in this instance down to about minus 12 to add heat to the tank. But in the evening, everyone comes back and people maybe aren't having showers, having huge hot water draws from our storage tank in the building. Maybe people are running dishwashers, doing laundry, doing some cooking. Suppose we had a 25% draw of hot water from the tank. So we deplete 25% of the volume going out to the taps in the building. We fill that back up, this 25%, with water at minus 10 degrees Celsius. Well, now our average tank temperature is about 47 degrees. So if we want 5 degrees above, and say we want the heat pump to have at least 52 degrees to add water to the tank, well, now if we look at the operating envelope for the heat pump, you'd say, well, now we can add heat to this tank down to about minus 3 degrees. So it can still work, but you're not necessarily going to be shifting as much of the usage away from natural gas to the heat pump with just one indirect tank. But the other point as well is there's no heat pump technology on the market that's going to be able to maintain the same recovery rates that typical domestic hot water systems are designed to without a lot of storage. That's the other part of the equation that we need to look at. But if you have an instance where, maybe the building's storage tank is undersized, well, the heat pump's not going to be able to instantaneously heat water up from 10 to 60 degrees. But the boiler, natural gas, is still able to maintain a high recovery rate. So I think it's important that we continue to do hybrid systems, especially for domestic, to be able to have high recovery rates in our systems without needing immense amounts of so preheating is one really good way that we can still leverage the heat pump, and we're going to be able to add more heat to the tank from the heat pump instead of natural gas. So we'll just have a preheat tank piped in series to that same tank that was served by the boiler. So we might have domestic going out to the building at 60 degrees, but now we're going to maintain this tank at, let's call it 30 degrees. So that same example that we just went over, whenever we decrease 50% of the volume in the tank gets used up. So this tank here, 50% of the water goes out to the taps. It gets filled from the preheated water. And now we fill this tank back that was at 30 degrees, but now it's being filled up halfway with 10-degree water. Well, now the tank's at 20 degrees. But if the heat pump's able to give you 35 or maybe 40 degrees, it down at minus 15 or 20, the heat pump's always going to be able to add heat to this tank, even in that 50% draw scenario. And even if we have a small draw from the tank of 25% draw, our average tank temperature now is 25 degrees, and the heat to be at a supply temperature 10 degrees above that. So we're going to get good heat transfer, and we're going to use the heat pump for more of the time throughout the winter and leverage that, still working within the capabilities of the heat pump with a lower supply temperature, but still offsetting hot water that's otherwise served by a boiler. If we look at the actual domestic hot water storage tank, though, because we're putting in preheated water that's at 30 degrees going into here, and this tank's maintained at 60, well, now even if we have 100% draw from the system, we're still filling this tank back up with water at 30 degrees. So now our boiler's only ever doing a lift from 30 to 60, or if we have these smaller lifts, the average tank temperature might only go down to 45 degrees. So now the boiler's doing a smaller lift. So we're kind of shifting the load that way as well. So we do need to think a little bit more holistically about the solutions that we're using in our buildings. So domestic hot water as well, in the summertime, we get really high efficiencies. So this is actually a water loop heat pump system example. And this is the last thing that I'll finish off with because we're coming up to time and want to make sure we have time for questions. But I just want to illustrate here at a constant flow rate at minus 15 for space heating water for maybe a cascade system, we'll have 140 kilowatts from a heat pump and a COP of 2.3. But if we run the heat pump in summer at 20 or 30 degrees ambient, we'll get much higher delta T's. So instead of 5, we'll get a 12C delta T, and we'll get 240% more capacity and COPs upwards of 4.5. So domestic hot water, we have usage year round. So that's also part of what we need to do for decarbonization. And that was pretty much it. I did want to talk about economics, but we're up to time here. I had a little bit too much information here. So anyway, we'll answer any questions that anyone might have.
Thank you so much, Chris. I will help with the questions here. So we have a question from Tim Short. So his question is, could you consider an interior installation of heat pump for domestic hot water? Yes, there is some heat being stolen, but won't the domestic hot water heat pump be able to leverage better than the loss?
Yeah, in British Columbia market, we see heat pumps being installed inside. They'll actually put them in parkades on the exhaust shafts, and they'll kind of use that residual heat. There's also types like these commercial heat pumps I was talking about. You can actually get them in ducted versions. We don't offer them at Mitsubishi, but there are some available on the market where you can actually install them inside and duct outside air to it. And you might be able to put a louver on that as well to kind of, if you have exhaust hair, because any exhaust that you have going outside from the building is wasted energy. So if we can recover it, we could definitely take advantage of that with a heat pump.
Awesome. Does anybody else in attendance have any other questions they want to ask? We have about 53 seconds left in our timer. Alrighty, I'll give you guys a couple more seconds to jump in with any questions. While we're waiting, I'll just let you guys know as well. So we have 2 more sessions coming up right after this. So we have John and William. They will both be speaking on air source heat pumps from a residential perspective. And then we have Michael Ridler, and he will be talking about hydronic design. So to enter those, you can just go back to the main lobby, and you should be able to join in pretty simply, just exactly how you did for this one. Just trying to delay it so let's see if we have any more questions coming in, but I don't think we do. So I want to thank you again, Chris, for your presentation. That was fantastic. And to reiterate another question, we will be having the recording of all the sessions after, which you all will have access to. So thank you, and hopefully you guys can join in on the next session. Thank you again, Chris.
Thank you. Thanks, Leah. All right. Enjoy the rest of the conference, everyone.